Okay, so the first part of our lab is going to be the reaction at the top. So we have cobalt chloride equilibrium mixture. So that's this big purplish bottle. Now I have gone and put a bit of this equilibrium mixture in 5 test tubes. That's done. Before we do the lab, we want to figure out what are our stresses doing in terms of adding or removing a product or reactant. And we want to know our color changes. So as soon as we see a color, we know which way it shifted. So I'm going to start with cobalt chloride, our very first reactant. And cobalt chloride is the first in our table. That chemical is blue. Okay. Water certainly isn't in our table, that's clear. So our reactant side is going to be blue and clear, so we're just going to see blue if we have only reactants. If we have just products, that cobalt water complex is going to be a pink color. Now, chloride isn't in our table. Ocean water is clear because chloride ions are clear. And this is an exothermic reaction, so we have an E term written in, but energy doesn't have a color. It's not something we see. So if this equilibrium is all reactants, we're going to see blue. If it is all products, we're going to see pink. And right now, we're seeing a purplish color because this reaction is somewhere in the middle. There's a bit of reactants and there's a bit of products. Now, the stresses that we're going to do to this reaction are down below. Okay. First, we have our control. We want to have one of the original that we can compare back to. So that I'm going to call either a light pink or purple. I'm going to call it light pink. Okay. We're not going to do any analysis with that. Again, it's just to compare back to. In our first trial, we're going to add water to our equilibrium mixture. Okay, so I have a dropper bottle with distilled water. So that'll be first. When we add water, in terms of Le Chatelier's principle and what stress we're doing, water is a reactant. Okay? So in this stress is going to be adding reactant. Okay? And we're going to see what happens when you add a reactant. Does it cause the reaction to shift forward, where it would see pink, shift backwards, where it would say blue, stay blue, or if nothing happens, it would stay the color of the control. The next stress, we're going to add silver nitrate. Now, when I look up to silver nitrate, I don't see silver or nitrate in any one of the reactants or products. When you see a stress on a test, exam, or lab that is not in your reaction, you should be thinking, what is it going to remove? If I add an acid, that would remove a base in our reaction. If I added a base, that's going to remove an acid. If I add something that isn't an acid or a base, it's most likely going to precipitate something out. Okay? And so you may need to flip to your solubility table. Now, you're really not going to need to, because as a teacher, I'm going to go through the key ones that the tests and the diplomas would cover. So I'm referring to this solubility table. If you check that table, nitrates are soluble with everything, but silver precipitates chloride. Okay? So that chloride ion is going to turn into silver chloride and fall to the bottom. Okay? It's not going to be removed from the test tube, but it's going to be removed from the equilibrium aqueous phase. So adding silver nitrate is going to remove a product. And again, we're going to look at the end of all of our experiments, is there a pattern for adding a reactant? Is there a pattern for removing a product? Okay. Next, we're going to heat up our equilibrium mixture. So I have some hot water that I've boiled, and then I have an ice bath that we can put it in. In terms of heating it, heating is going to add energy. Okay. Well, we see an energy term. So heating it is the same as adding a product, because energy is a product or something produced from this reaction. So heating is going to be add product. Okay. Again, we're thinking of that energy term as another chemical species. Cooling it is going to do the opposite. It's going to suck energy out of our equilibrium mixture. Okay. Because that E is a product, we're going to be removing some of that product. So let's carry out this reaction, and we'll do both the observations and the analysis. Okay. So for the first one, let's add water. So here's our equilibrium mixture. Again, it's in the middle. Let's just recap the colors. If it shifts to reactants, blue. If it shifts to products, it will turn pink. Okay? So this system is at equilibrium. We're going to mess it up, and it's going to go to a new equilibrium. Just confirming, I do have my distilled water. And I'm definitely not seeing any blue. Add a bit more. Yeah, no blue forming at the top. I'll give it a shake. And we're seeing, if anything, it's a little bit more pink. So for observations after the stress, it is still a light pink. So either it didn't do anything or it shifted a little bit more towards the products. Now, there was a very faint change. It was hard to see, but I believe it went a little bit more pink. Now, pink is the product side. So when we added this product, it going pink in terms of a shift, that would be forward. Okay, there's no way this shifted backwards. If it went backwards, we would see blue forming, and we didn't. Let's move on to removing a product with silver nitrate. And again, those my right hand, this is the control. This one was the one we added water to. So next, silver nitrate. So I'm expecting a precipitation reaction, but that's not the color change I'm after. I'm like, does it stay pink or does it go blue? And there's that precipitation I was expecting. Silver chloride solid is white. So I'll give this a good shake. You can pretty clearly see a whole bunch of white precipitate at the bottom. That's not the color I care about. I care about our equilibrium mixture. And this one is even darker pink. I'll grab my control again. There's a very distinctive difference. This looks even more purple now, the control that I'm moving up and down. And the forward one is our reaction. Definitely pink now, no purple at all. So it's definitely shifted towards the products. So doing a little bit of analysis, if we added a reactant, it went away from it towards the products. If we took a product away, it went back towards the products. Okay. Next, we're going to heat and cool. Now, I find this the most interesting part, and I can really convey the notion of equilibrium. I'm going to grab my thinnest test tube. So next is heating, and this would be adding a product. Now, it takes a little bit of time for that heat to transfer. But right away, I'm starting to see something. The top is turning blue. Let's see if that's what happens to the whole solution. Hopefully you can see that blue color forming. Yeah, definitely a blue color. It is not pink anymore. So when we added a product, we're adding thermal energy or heat, it shifted towards the blue. So we add a product, our observation is blue, and our shift is reverse because blue means that's a reactant. So it had to shift backwards towards reactants. So that's the opposite. We removed a product, it went towards the product. We add a product in the heat case and it shifted away from it. So I'm going to take the same, my thinnest test tube, just drying it off. So it turned blue when I heated it. Let's see what happens when I cool it. And I grab the exact same test tube. And I can already see some pink forming at the bottom. Now it's probably hard to see through the ice. Yeah, some of the blue is gone. It's now more of a purple. Quite starting to be pink now. To me, it looked half purple, half pink last time. And now it is quite pink. So when we take away a product, and this is the second time we removed a product, and in both cases, it shifts towards products. Shift was forward. Pink is a product, so the reaction must be making more products. Now, while I was writing that down, I threw this test tube back in the hot water. We don't need to record this again, but we're seeing it turn blue. I could go back and forth over and over again, and this would keep changing color. Blue in the hot, turn pink in the cold. Okay. So we're into an equilibrium unit. Equilibrium reactions can go both ways, and there's no limit to how many times. As long as you don't lose the reactant or product, it can potentially shift over and over again. So that's our first experiment. We'll move to the second. So this one is with the HTB indicator and 5 mils of water. Now this indicator is a diprotic indicator. It can, depending on how many H's it has, have 3 different colors with 2 H's, 1 H, and no H. So I've pre-put in 2 drops of indicator. So HTB is our indicator, 2 drops are put in already. And I have a base and an acid to add in. So let's predict the shifts before we add in our acid and our base. Sorry, do the colors, then predict the shift. So H2TB is right there. If we have all reactants in reaction number 1, we would see a red color. Okay. If that top reaction 1 shifts to products, we have 1 H, and that is going to be yellow. Okay. Now our second reaction starts with that same species, so that's yellow. Okay. And if it loses its last H and goes to just TB2 minus, then we're going to see a blue color. At the very beginning, we have a yellow, so it's primarily the HTB is what's in this solution right now. So we're either going to see it shift red, where we'll use the first equation, or we'll see it shift blue, and then we'll analyze the second. We're not going to have to analyze both of these at the same time. Okay. So let's think, what would happen in terms of our prediction if we added acid? Well, acid would be adding H+. All acids are going to produce H+ in solution. Sometimes we write it as hydronium, H3O+. H+, no matter which reaction we look at, H+ is always a product. So if we add H+, no matter which reaction we look at, this is going to be an add product. When we add base, all Arrhenius bases are going to produce hydroxide in solution. We have no base in this balanced chemical reaction, so adding a base isn't adding something, it must be removing something, and that's going to neutralize, use up our H+. H+ is always a product, so this is going to remove product. Okay. So let's see what happens. Again, I'll just make a little note that our control is yellow. So we're going to start with the acid. This is 0.1 mole per liter hydrochloric acid. Okay. The Cl- that I'm going to add will do nothing. Chloride isn't in the reaction, and chloride doesn't precipitate anything. So there's our equilibrium mixture. Looks a little pinkish on the top. Let's add more. And it has definitely turned a pink color. So our observation is we're seeing a pink. We don't have any pinks here, but that pink is probably the early sign of red. If I kept adding more, the pink would get darker and turn into a red. So what is our shift? Pink in equation number 1, or red in equation number 1, yellow to red would be going backwards. So if you add a product, it's shifting away from that product to use some of it up. The last part, we'll add a base. I'll first do this to a new mixture. So I've got yellow. Add a few drops, and it looked like a little bit of blue formed on the top. Let's add some more. Yeah, it is a nice blue. So blue is on the bottom, so we did yellow to blue is going towards products. So just highlighting that shift was from what I've labeled equation number 1 for the adding the acid, and equation number 2, or sorry, for the base, it's equation number 2 shifting forward. So we removed a product, it's shifting back to replace some of what we removed. Now I can even do this. This isn't something we're going to put in a report, but if we take this red and I add acid to it, it should shift from red to the yellow species when there's one H, and then when I get rid of all the H's, there should be no blue. Sorry, it should shift totally to blue. So let's see what happens when I... Now I see this bit of blue, and then as it mixes, it goes away. I've got there. The red is starting to go away. Oh, now we're really starting to see the blue. So I went from red, I added it so quickly, we went flying through the yellow to the blue. Okay. Again, we're not documenting this one. That's experiment 2 of 3. We'll move on to what is labeled part 4. Cobalt complexes. I've got some ammonia that I'm going to add to make the equilibrium mixture, then add even more ammonia, and then I have some hydrochloric acid again. This is 1 mole per liter, so stronger than before. This would be a pH of 0. First is to figure out what the colors mean. So copper complexed with water is down there. That's a pale blue. Okay. Ammonia, we don't have in a table, but we have some in a bottle. It's a brown bottle, but it is a clear solution. There is some in the eyedropper, and there is no color to it. So I'm not going to write anything clear on my board. Copper ammonia complex is a very deep or dark pink, dark blue, sorry. I know the notes say deep, but I think dark blue is a better way to convey it. And then we have water, which has no color. So if this equilibrium shifts towards reactants, we'll see a light or pale blue, and we'll see it get deep or dark as it shifts towards products. Now in this one, we have to make up the equilibrium mixture first. So the control is not these. This is just copper sulfate, and I need to add a couple drops of ammonia to make our equilibrium mixture. So the procedure asks me to put in 3 drops. Okay. Now this has copper and ammonia, and I'm going to shake it, and fairly quickly it's going to go to equilibrium. Okay. So our equilibrium mixture is starting with the paler blue. Okay. Okay. We're going to add ammonia, which is NH3, and ammonia is one of our reactants. So that is going to add reactant. Our second stress is going to be adding hydrochloric acid, which is not there. There's no H or Cl minus, so it must be going to remove something. Well, hydrochloric acid is an acid, it's right in its name, so I'm looking for any basis, and ammonia is a base. Okay. Okay. And we'll talk, discuss the fact that ammonia is a base in the further later on in this unit. So we're going to remove ammonia. We're going to turn ammonia into ammonium. So because ammonia is a reactant, we're going to remove that. Okay. We won't have NH3 anymore. We'll have NH4. So let's carry these last 2 pieces out. So here's my equilibrium mixture. I'm adding ammonia first as a reactant, and we're looking for the darkness of the blue. Now, the reaction will happen at the start, at the top, sorry. Now I'm seeing a dark blue form right at the top, and it just hasn't had time to work its way down. Let's see if we get that dark blue throughout the whole solution. Hopefully you're seeing that dark blue on the top. It's most prevalent when you look down on it. Hopefully that helps to see that it is turning a dark blue and working its way all the way down. So adding that reactant is making it go dark blue. Dark blue is a product. So it's a product, so it's a shift forward. Okay, we're almost done, and when we get to the evaluation, you're going to look at all of the add reactants and all the add products. So I'm going to take this same mixture that I got to shift towards products and turn dark blue after leaving it. Now the whole thing is a nice deep dark blue. Let's see what happens when I add hydrochloric acid to this. We're expecting it to remove that ammonia. Looks like it got a little lighter on top for a second. Let's set the paper towel. Now I added a lot of ammonia, so it's going to take a bit of acid to see our shift. And yeah, the dark blue is fading. And we're back to that light blue. Now, solutions don't mix well in these test tubes. They take good shaking. And yeah, that dark blue is definitely gone. And we have a nice light blue color again. Light blue is reactants. So that concludes our last trial. Again, just to emphasize Le Chatelier's principle again, I got this to shift towards reactants. We already know that ammonia is going to make it shift towards products. So if I dump in enough ammonia, I should be able to get it to shift back to that dark blue. And yeah, I see that dark blue at the top right away. So it is going back. It's not just a shift once. It'll shift over and over again. Okay. Now my volume keeps going up and up. I have to use up all that hydrochloric acid to get the shift. And there is our dark blue forming. Probably just needs a little bit more ammonia to get the whole thing really dark. Okay. So that is our lab. Let's do, because this is a learning lab, I want to start the evaluation together. So this is all you're going to conclude for me. There's no calculations to do. We've already done some of the analysis right in that observation table. I didn't separate it out. And the reason I didn't separate it out was I want you to see the observation and the stress right away and not make you do it in a separate section. So let's look at every time we added a reactant and see if we can predict the outcome. Is there a trend or is it random? So I'm going to flip back through our data. See, do we add a reactant? We did. Here we added a reactant and it shifted forward. Going down into our second experiment. We didn't add any reactants in the second experiment. So I have, from our first two, we just have one shift forward. From our last experiment, we have another add reactant and it did the same thing, shift forward. So it looks like when you add a reactant, you get a forward shift. No, I'm not going to use words, I'm just going to use the arrow to show my shift. Let's see if there's a pattern for removing reactant. Okay. No remove reactant in the first experiment. The next one, no remove reactant. We have a remove reactant, and our very last one, it is shifting reverse. Okay. Well, that probably makes sense. We don't have a lot of data points, but if we add a reactant, we get a shift one way. If we do the opposite, we remove instead of add, the shift goes the other way. So it looks like there is a bit of a pattern, and there is a very distinctive pattern to Le Chatelier's principle. Okay. Let's finish this. Now you're going to have to articulate these arrows into words and write about a paragraph each or a couple sentences for each of these boxes. Let's see, add a product. Let's go back through all our data. We added a product with the heating and it went backwards, so we got to remember that. Add a product again. We added a product with the acid and we went backwards also, so that's consistent. And that's it for adding products. Okay. So both of our trials, when you add a product, it went in the reverse direction. So let's see if we have a bit of a pattern, and then we'll do the last one. Okay. If we add a reactant, it's shifting away from it. Okay. So we're going to get rid of that reactant. If we remove a reactant, it's trying to put it back. Okay. So it seems to be kind of doing the opposite to whatever we do. Let's see, if we add a product, it goes away from the product, so it tries to get rid of it. Okay. What would happen if we continue that trend? If we remove a product, we would expect it to try to replace it. Okay, when we removed a reactant, it tried to replace the reactant. If we remove a product, I'm thinking it's going to want to try to replace the product, which should go forward. Let's see if our data suggests that. So remove product. No data points there. Yeah, we have remove a product, and it did in fact shift to replace it. Okay. So everything is kind of seeming to lead towards some sort of opposite pattern. Whatever you do or somebody does to an equilibrium system, it seems to want to shift to do the opposite. Okay. And that is the whole point of this lab, for you to see that experimentally. Le Chatelier's principle, the heart of it, paraphrasing, is whatever you do to a system, the equilibrium will shift to try to undo or counter what you did. Okay. And that concludes this lab.